there's a famous Feynman line that everything is made of atoms. But weirdly, the Big Bang didn't have any atoms. So what gives? How the heck did the first atoms form? So I've been down the rabbit hole in this, and it's kind of a hard rabbit hole to go down because you're dealing with physicists. And so they talk about all these things that happen in a trillionth of a second. They talk about all these strange things like quarks. And hopefully today I'll be able to share with you what actually matters for us normal people. And it's good because it'll feel good to understand how the heck did atoms form, and then you could share it at your next dinner party, or when new news comes in around fusion reactors, or if you want to go work in particle physics, it'll be helpful then too. That's actually a funny energy. Reese at a dinner party. People are saying, oh, LeBron James, is he the GOAT or not? And I'm like, did you guys know? How did the first atoms form? No one cares. But yeah, let's dive into today's episode of How Everything Evolved. Okay, so every episode of How Everything Evolved starts with the timeline. And we have, the beginning of time and then now. And this is 14 billion years ago. This is now. And so today we're going to dive into right here. We had the Big Bang, and then here is roughly 1 million years after the Big Bang. So there's some things that happened in the first few microseconds, and then there's some things that happened quickly thereafter. And by quickly, I mean in the hundreds of thousands of years. And so the core puzzle behind today is, well, we know that we eventually have all these atoms. And we know that the Big Bang, that the Big Bang doesn't have any atoms. And so how the heck did we go from no atoms to lots of atoms? That's actually a really interesting question. And so we can investigate this by diving into what is an atom. And I think we know that an atom is composed of two things. There is the protons in the middle, and then on the outside there are the electrons. And the electrons, they orbit around the proton in the nucleus. And obviously this is an electron cloud, not just an electron, but not just an orbiting electron, but this is roughly the structure. And so when we're trying to understand how everything evolved, we can say, well, okay, we need to have the protons and the protons, and protons didn't actually exist at the beginning of the Big Bang. And so we need to understand how that happened. And then the other thing we need to understand is how the heck did we get the electrons to be orbiting around the protons? That also wasn't happening at the beginning. So let's look at each of those. Let's zoom in, let's go over here, and let's say, okay, let's talk about protons. And how the heck did the first protons form? So this is... The first question here is, what is a proton even made out of? And this is a funny thing because I think over time, if you look at, in the early 1800s with Dalton and everybody, they were first finding out maybe things are made of something. They don't just have an essential quality to them. And maybe those things are a very small thing. And we're going to call those things an atom, aka atom, it means to chop in half, like a tomahawk, and A means not chop in half. And so we said, wow, maybe these things are made of atoms. Maybe everything is made of atoms, a thing that you cannot go deeper than. But over time, we learned that, no, actually, you can go deeper than this. Atoms are made of, as we showed before, there's, protons and neutrons in some kind of, protons and neutrons in the nucleus, and then electrons orbiting around them. And so we learned about those kind of core components. But then over time, especially in the 1900s, and I think this was later, this may have been even after World War II, I don't remember the exact timeline, we said, oh, actually these protons, when you shove them into a particle collider, those two are composed of smaller pieces. And so those things are called quarks. And the term quark is kind of dumb, and I don't know why. What they were smoking at the beginning of particle physicist time, but probably a lot of stuff. And they said, okay, so we call these things quarks, and quarks are part of the standard model. So you can see here is our beautiful standard model. And the standard model is confusing. It has stupid names like fermions and bosons and quarks and leptons. But it's actually, when you get down to it, it's relatively simple. So the key idea here is that the things on the left are particles, three generations of matter, and things on the right are forces, like gravity and electromagnetism. So that's the idea. And a quark is, these things up top here. Another key part of this graph is, or this little chart, the standard model, is to ignore the second and the third columns. Those things are just heavier versions of the things that we know and love, like electrons. So you don't really need to think about muons. You don't really need to think about tau. Just think about electrons. So we're looking at this first column here, up and down quark, and then electrons and electron neutrinos. We're going to mostly talk about up and down quarks today with a little bit of electrons. So these quarks, the up and down quarks, are what a proton is composed of. And so if we go back to this image here, you can see that there's a quark, these little up and down quarks. They are, you can have a little up quark, and you have a little up quark, and you have a little down quark. And UUD. And these up quarks, they have a positive charge. The down quarks have a negative charge. And they are combined together like all good things. And that creates a proton. And so this is just like anything else. When you double click on a atom, you say, what is the atom composed of? Oh, it's composed of protons, neutrons, and electrons. When you double click on a proton, aka when you shove it into a particle collider, what comes out are these up and down quarks. And so a proton has two up quarks and a down quark, while a neutron has one up quark and then two down quarks. And you can again see the Y with the proton here, the pluses and the minuses cancel out, and then with a neutron, or the pluses and the minuses become 1, 4/3 minus 1/3, and then the neutron, the two pluses, it cancel out with the two minuses. So that is how a proton and neutron are composed of quarks. And at the beginning, the interesting part was that, if you think about these quarks, what keeps them together is actually what's called a gluon. So if we go back to our good friend, the standard model here, this red thing in the top, the gluon, this is the force carrier that keeps protons together, that keeps the quarks in a proton together. And so if we look at our little image here, essentially the way I think about it is that there's little pieces of glue that go in between the up quarks and the down quarks. And that's a gluon. And it's also, a gluon is part of what's called the strong nuclear force. Strong nuclear force. And the strong nuclear force, there's 4 forces. We know gravity, we know electromagnetism. There's one called, and there's a strong nuclear force and the weak nuclear force. And so those are the only 4 forces, which is kind of nice and easy. And to understand the strong nuclear force, this is what it does. This is, it is essentially Velcro. I love thinking it is Velcro, and it Velcros the quarks and a proton together. So that's roughly how this works. And by the way, you can start to, this I think makes this all less scary. You're like, oh, there's up and down quarks. They make a proton, and they're combined together by the gluon, aka the strong nuclear force, aka Velcro. So at the beginning of time, if we go back to way the beginning of time and back to the Big Bang, over here, we say, okay, what happened? And right after the Big Bang, well, what actually happened here is everything just there were only up and down quarks. There were lots and lots of up quarks and down quarks and up quarks, down quarks, blah, blah. But things were so crazy. There was so much energy in that system at the beginning that they couldn't freeze and they couldn't form down into protons and neutrons. And so this is called the Quark-gluon plasma. Which again is a great name, Quark-gluon plasma. And this was what things were like at the beginning, and then they very quickly, this is in the first couple microseconds, this is about 10 microseconds into the Big Bang, the quark-gluon plasma froze down, and we went from a time where everything was just going crazy to just normal protons and neutrons after that point. And so this is 10 microseconds. And so that was kind of the first key thing, is we had to create protons and neutrons, and we did it by the quarks and gluon plasma finally settling down in those first 10 microseconds into our beautiful protons and our beautiful neutrons. So that is the first part of creating atoms. And the second part of creating atoms is, we need to make the, if we go over here and we say, okay, the electrons need to orbit around these, the protons. And so at the beginning, all that we had is the electrons essentially had too much energy in them. And it was crazy. And so this was it was called an ionized plasma. Ionized plasma. And I think that the word plasma is kind of funny. It sounds weird. Plasma is like the fourth kind of matter. There's solid, liquid, gas, and then plasma. And plasma is when you have an ionized, means that the electrons around a nucleus have been shot off. And so at the beginning, when these electrons, they can't be held onto that proton. And so they're just kind of existing, not attached to an atom. And so we have this ionized plasma happening. There was a few minutes in, let's call it 5 to 20 minutes after the Big Bang, we had what was called Big Bang nucleosynthesis. Big Bang nucleosynthesis. Big Bang nucleosynthesis. And this is when we got, much later to create the rest of the periodic table, which we'll chat about next time. That happens in stars. But at the beginning, we had essentially there was only hydrogen. Lots, the Quark-gluon plasma became a bunch of these protons and neutrons. And we had initially just a bunch of hydrogen, but then that hydrogen, some of it turned into helium. And so we got, hydrogen is just one proton, while a helium is 2 protons and 2 neutrons. And so at the beginning, this essentially gave us roughly the composition of elements that we see in the world today, which is 75% hydrogen and 25% helium. And then 1% the rest of the elements all combined. And so this Big Bang nucleosynthesis happened. We got these hydrogen protons, and then we got these helium nuclei, but they still didn't have the electrons on them. And so eventually, in order to get that atom, you need to have the electron actually going around it. And so eventually, around 380,000 years after the Big Bang, eventually it became cool enough for the electrons to exist around the nucleus. And so that was a beautiful moment, and it's called recombination. And it's a fun moment because it's like coming home again. The electrons get recombined with their friends. And so that turned us, and that gave us atoms, and that gave us essentially the state of the universe, which happened for the next kind of billion or so years, was this universe of hydrogen and helium nuclei with electrons going around them, aka the atoms we know and love today. So that was a really cool moment. And I think that it was, if we go back to our standard model here, you can see we're starting to fill it out. And so there's the electron here. That's another piece of our standard model. It's a lepton. It doesn't combine into bigger things like up and down quarks do. And it's almost massless, but it's not quite massless. It does have a mass. And then over here's our little photon. The photon is the carrier of the electromagnetic charge. So that's very cool. And it also, there's the other cool thing that happened at this time was, if we go back to, it was initially the Big Bang. The Big Bang was a crazy moment. And during this time, we had all these protons and all these electrons all around, and nothing could really, there were a bunch of photons in there, a bunch of light in there that couldn't really escape because it was, everything was too muddled. And so you can imagine some version of muddling, where it's like, something ish like this, where everything was, it looked like that. And so it was too muddled, but then once the Big Bang nucleosynthesis, once the recombination happened, then photons could actually move more easily through the universe. And so they did. And this gave us, at 380,000 years ago, and so what this gave us is those photons were able to fly freely, and it gave us the cosmic background microwave radiation, CMR or CMBR. And this is that famous image where you say, whoa, here are these first photons from the very, very beginning of the universe, when they finally got to escape right after recombination, right after the universe became clear. These are these amazing photons that have been ridiculously redshifted. They're redshifted to like, they've been they're very, very red now. And we can see them from the beginning of the universe. And that's one of the ways that we know what happened at the beginning of the Big Bang. So that's how the first atoms formed. We had, in that first microsecond, the quark-gluon plasma combined to form the first protons and neutrons. And then, 380,000 years later, the electrons recombined. There was recombination. They combined onto hydrogen and helium atoms, hydrogen and helium nuclei, giving us the first atoms of the universe. And this is a beautiful moment. It shows us, it helps us understand the strong nuclear force for the first time. It also helps us understand the electromagnetic force for the first time. And it shows us a thing that evolution likes to do in these environments, which is to select for stable, a survival of the stable. And over time, we're going to get more and more stable forms coming, more elements, more stars, more macrostructure. And so that's what we're going to look at next time. Is we're going to not only have microstructure, but we're going to have the macrostructure where these clouds of atoms turn into stars. And we'll learn about gravity in that time. And then we'll also, as stars happen, they give us the rest of the periodic table. There's not just hydrogen and helium, but there's 118 elements. And so we'll look at all those elements and how stars form all of them deep within their cores, which is really pretty cool. Thank you so much for listening. Thank you to my patrons on Patreon and to the supporters of Root for supporting this educational content. And if you want to learn more about how everything evolved, feel free to subscribe for more. And bye. Thanks.